So, good afternoon, students. This is Arvind, Assistant Professor, Department of EEE, DBS IT Kavali. So, in the previous class, I discussed about three-level converter operation and fundamental and harmonic components of three-level converter. And now, in this class, I'm going to discuss three-level converter with parallel legs. And next, I'm going to discuss pulse width modulation converter. So, these two topics I'm going to cover in this class. So, firstly, we will see the three-level converter with parallel connection, okay, with two parallel legs. Okay, let's get into the topic, that is, so that means three level converter with parallel legs is yet another method of achieving a three level converter, which is to connect two phase legs in parallel per phase. Okay, which is to connect two phase legs in parallel per phase. So in the previous class I discussed about three level converter. So in that one, same diagram is there, but one small difference is means in that case we used only one phase leg, but here we are using two phase legs. Why means here we are taken parallel connection. That's why to connect the parallel means we have to take two phase legs. Okay, that's why here I am taking two phase legs in parallel per phase. Okay, the diagram is like this. So this is the diagrammatic representation of three level converter with parallel legs. So if you observe this diagram, so here I am taking two phase legs. Okay, so each phase leg consists of two converters. Okay, each phase leg consists of two converters, one at the bottom and one at the top. Okay, and in between these two, that means in between these two phase legs we have one inductor. So by using this inductor we will join these two, connect these two phase legs, and this, from the midpoint of the inductor we are connecting this midpoint of the inductor to the AC side. So if you observe on the DC side we have two capacitors. Okay, and these two capacitors are uh, connected by the neutral point N, that is on DC side. So it consists of voltage, that is plus Vd by 2 and minus Vd by 2. Okay, next, so the two legs are paralleled through an inductor. So I already said this point. The two legs are paralleled through an inductor and the AC connection is made at the midpoint of this inductor. Okay, and their pulses sets are phase shifted by an angle alpha, each in the opposite directions. Each in the opposite direction. So in one direction we have alpha and in another direction we have another alpha. That means total we have two alpha. Okay, total we have two alpha in different directions. That means in opposite directions. Okay, next, coming to the operational waveforms for a three level converter with parallel legs. So in the first two waveforms, so actually we have four waveforms to explain this three level converter with parallel legs. In those four waveforms, first two waveforms belongs to AC terminal voltage of the two phase legs, AC terminal voltage of the two phase legs with respect to a hypothetical DC midpoint. Okay, that is belongs to first two waveforms, and those two waveforms shifted from each other by an angle 2 alpha, by an angle 2 alpha. And next, the net AC terminal voltage with respect to the DC midpoint, okay, is the average of the two voltages. So actually in the third, I am discussing about the third waveform of that operational waveform. So the third waveform appear. Why? Because the net AC terminal voltage with respect to the DC midpoint is the average of the two voltages and is shown by the third waveform. And the third waveform consists of a half cycle pulse of variable duration, that is sigma. Variable duration sigma is equal to 180 minus 2 alpha. 180 minus 2 alpha. The same as for the three level converter with the split capacitor discussed above. That means in the operation, in the main, the three level converter operation, we are using the same diagram. So I already said this point. So this diagram also used in the previous three level converter operation also, but at that operation we are used only one phase leg, but here we are using two phase legs. That is the only difference. uh, in the three-level converter operation and three-level converter with parallel operation. That is the main difference. Okay, and next, so these are the waveforms I am discussing. The first two waveforms gives the AC terminal voltage. AC terminal voltage with reference to the neutral midpoint. Okay, with a duration of 2 alpha. Okay, next, a third waveform. I already discussed this one. So this waveform gives the net terminal voltage. Okay, with a period of sigma that is equal to 180 minus 2 alpha. And the fourth waveform gives the inductor voltage. Inductor voltage waveform. Fourth waveform is inductor voltage waveform. Okay, so I will discuss this fourth waveform in the next slide. Okay, so coming to the harmonic content is the same as shown by the figure 3.9. So that is, in the previous class I discussed about three-level converter. So in the three-level converter I discussed about fundamental and harmonic component of the three-level converter. So at that time I shown one diagram. So that is a diagram to represent the harmonic components of a three-level converter. So in the diagram I shown you like it looks like a box. Okay, one rectangular box. On the left side y-axis we taken that the fundamental harmonics. Okay, fundamental harmonics in per units only, in per units. That means 0.1, 0.2 and so on, 1 per unit. On the x-axis we are taken that sigma value, that is sigma is equal to 0 to 180 and 180 to 0. Like that we taken those things. So here also the harmonic content is same. Three-level converter with parallel X and three-level converter operation, main operation, the harmonic content is the same. Okay, and the inductor voltage is given by, I am talking about the fourth waveform. In the previous slide I show you a waveforms for a three-level converter with parallel legs. On the last waveform I am discussing the topic. So the inductor voltage is given by the difference of the AC voltage of the two legs and is shown by the fourth waveform. Okay, so which conveys that greater the required range of control, larger would be the inductor size. Okay, next its MVA rating would be directly proportional to integral of the voltage VL. Okay, its MVA rating would be directly proportional to the integral of the voltage VL, that is the inductor voltage. Okay, next, so it is natural to suppose that one can go to higher levels, that is 4 level, 5 level and so on. So actually we are dealing with 3 level, but here it is natural to suppose that one can go to higher levels. So that means if it go to 4th level or 5th level and so on. However, detailed consideration of these higher level topologies would reveal a major problem of voltage balance between the capacitors. Problem we are facing. If the levels are increasing, that means from third level to fourth level, fourth level to fifth level, fifth level to sixth level and so on, at that time we will have a major problem of voltage balancing between the capacitors. Okay, so it is not reasonable to assume that the current flow through each level is balanced with in some tolerable range for a converter to continue to operate in 5 level mode on its own. Okay, so it is not reasonable. Okay, next, however, if there is a two converter system, so however, if there is a two converter system, okay, forget about 3 level, 4 level, 5 level. So here, if there is a two converter system with DC bus in between, it is possible to link the two converters in a way to ensure balanced capacitor voltages. So by using two converter system, we have to balance capacitor voltages. Okay, next, however, if there is a two converter system, suppose if you take the two converter system with the DC bus in between, it is possible to link the two converters in a way to ensure balanced capacitor voltages of different levels. Okay, not for one level, we will balance capacitor voltages of different levels. Okay, not a 2 level, not a 1 level, not a 3 levels, like that. if we take the fourth, fifth levels, also we will balance somewhat. Okay. Next, we will come to topic, that is pulse width modulation converter. Shortly, we will call it as PWM converter. This is also very important topic in this chapter. So in two level or multi-level converters, there is only one turn on, turn off per device per cycle. You already know this point. So in a two level or multi-level converters, there is only one turn on, turn off device per cycle. Okay. So with these converters, the AC output voltage can be controlled. So by using those converters, the AC output voltage can be controlled. So by varying the width of the voltage pulses, and the amplitude of the DC bus voltage. Okay, by using amplitude of the bus voltages and width of the voltage pulses, we can control the AC output voltage. Okay, and next another approach is to have multiple pulses per half cycle. So another approach is also there. That is, another approach is to have multiple pulses per half, and then vary the width of the pulses to vary the amplitude of the AC voltage. Okay, at that time we have to vary the width of the pulses. Why? Because to vary the amplitude of the AC voltage. Okay, next, the principal reason for doing so is to be able to vary the AC output voltage and to reduce the lower order harmonics, as will be explained here briefly. So in this topic we will discuss this one. Okay, the principal reason for doing so is to be able to vary the AC output voltage and reduce the low order harmonics. Okay, next, so it goes without saying that more pulses means more switching losses. So if we have more pulses, we have more switching losses. So that the gains from the use of PWM, that means pulse width modulation, have to be sufficient to justify an increase in switching losses. Okay, to be sufficient to justify an increase in switching losses. So there are also resonant PWM converter topologies that incorporate current zero or voltage zero type soft switching. So in order to reduce the switching losses. So why? Because we have more pulses means we have more switching losses. So to reduce those switching losses, we have to use different power converter topologies, so that incorporate zero current or zero voltage type soft switching. So by using these in order to reduce the switching losses. Okay, so such converters are being increasingly utilized in some low power applications. So these converters, that means PWM converters, are being increasingly utilized in some low power applications, but with the known topologies. Okay, they have they have not been justifiable at a high power levels due to higher equipment cost. Okay, next, so this pulse width modulation converters of low voltage and low power in the range of tens of watts for say on printed circuit boards, power supplies may have internal PWM frequency, that is pulse width modulation frequency, in the hundreds of kilohertz. Okay, next, industrial drives in tens of kilowatts. So industrial drives in tens of kilowatts may have internal PWM frequency in the tens of kilohertz. Internal frequency in the tens of kilohertz. So previously I discussed about PWM converters of low voltage and low power in the range of tens of watts. Like printed circuit boards, power supplies, these all are having internal PWM frequency in the hundreds of kilohertz, but the power range is tens of watts. But here in the industrial drives, we have tens of kilowatts power range, may have internal PWM frequency in the tens of kilohertz. Tens of kilohertz. So in the previous we have hundreds of kilohertz. At that time the power range is tens of watts, but here the power range is tens of kilowatts. So that's why it is having tens of kilohertz. That one having hundreds of kilohertz. And next, for converters in the 1 megawatt range, so for converters in the 1 megawatt range, such as for custom power, the frequency may be in few kilohertz range. Okay, next, so for fax technology with high power in the tens of megawatts and converter voltage in kilovolts and tens of kilovolts, low frequencies in the few hundred kilohertz. 100 hertz, not kilohertz. In the few hundred hertz or maybe the low kilohertz range may seem feasible and worth considering. Okay, for fax technology we are discussing. Okay, next consider again a phase lag. So here we are using one more phase lag as a part of three-phase bridge converter. As a part of three-phase bridge converter, so it is seems like three-phase. We discussed about one topic, that is a three-phase full-wave bridge converter. So this diagram also sees like this, like that diagram. So this is the diagram we are taking. So this diagram is equal to the three-level converter main operation, but in that one we have totally 8 valves, but here we have 4 valves. So in this arrangement we have two converters on single phase leg, two converters in single phase leg, and on the DC side we have two capacitors, and it is connected in between the midpoint of the neutral voltage, that is N, neutral point N, and the A point gives the AC side connection. So in between two connectors we have A point that represents the AC connection, AC side connection. And next, so here we have one diagram. So this diagram, okay. So this diagram shows comparison of two types of control signals. So this 3.10b means in the previous three-level converter operation. So I shown on waveforms, four waveforms we've seen. Okay, two waveforms for AC terminal voltage uh, that belongs to the midpoint voltage, neutral midpoint voltage, and another third diagram gives the AC terminal voltage average. And next fourth waveform is inductor voltage. So comparison of two types of control signals, three signals of main frequency sine wave representing three phases, and a sawtooth wave signal of 9 times the main frequency. So if you see the diagram waveform, so this waveform, okay. So first waveform, it is a sawtooth wave, okay. So here it shows a comparison of two types of control signals, okay. So three signals of main frequency sine wave representing three phases, and a sawtooth wave signal of 9 times the main frequency, that is 540 hertz for 60 hertz main frequency. So turn on and turn off pulses to the devices correspond to the corresponding crossing points of the sawtooth wave with the sine wave of corresponding phase. Okay, we have turn on and turn off pulses to the devices, okay, correspond to the crossing points of the sawtooth wave with the sine wave of corresponding phase. Okay, so this one. So this is a sine wave. So here we have some crossing points while drawing the sawtooth wave. Okay, so in the first waveform we have two waveforms. One is sine wave and another one is sawtooth wave. Okay, so the negative slope of the sawtooth wave crossing the sine wave of phase A result in a turn on pulse for device 1 and turn off pulse for device 4. Okay, the negative slope of the sawtooth wave crossing the sine wave of phase A result in a turn on pulse for device 1 and turn off pulse for device 4. So if you observe the diagram, you will understand. Okay, so the first diagram I am discussing. So the resulting voltage of the AC terminal A with respect to hypothetical midpoint N of the DC capacitor is shown in figure 3.11b. And that means the last waveform. The last waveform gives this one, the resulting voltage of the AC terminal voltage, AC terminal A with respect to the hypothetical midpoint N, that is VAN. Okay, of the DC capacitor is shown in hatch. Okay, square wave. That means second waveform. Okay. Next, So in comparison to figure 3.5b, that means in the concept of three-phase full-wave bridge converter operation. So in comparison to that diagram, with two square pulses per cycle, the waveform of figure 3.11b, that means previous diagram, is made up of 9 square pulse cycles of varying width per main frequency cycle. So is made up of 9 square pulse cycles of varying width per main frequency cycle. So this one, if you count, we have 9 pulses: 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 pulses on the above and 9 pulses on the below. Okay. So the pulses are wider in the middle of the each half sine wave, ends of the half sine wave. Okay, the pulses are wider in the middle of the each half sine wave compared to the ends of the half sine wave. Okay. Next, so the following observations are noting with respect to the waveforms of figure 3.1b, that means last diagram. Okay, those observations are: first one is the output voltage waveform contains a fundamental frequency component and harmonics. So you already know this point. The output voltage waveform contains a fundamental frequency component and harmonics. And next one is the output voltage pulses are symmetrical about the zero crossing of the sine wave. Zero crossing of the sine wave, because the sawtooth wave frequency is an odd integer multiple of the main frequency. Okay. Next, in the second point also we have any even multiple will create asymmetry about the zero crossing. So any even multiple will create asymmetry about the zero crossing, which will contain even harmonics. Which will contain even harmonics. In the previous we have odd integer multiples of main frequency. Okay. Next we have non-integer multiples are even worse as they create sub and super subsynchronous harmonics as well. Okay, non-integer multiples are even worse as they create sub and super synchronous harmonics as well. So when the frequency is high, above a few kilohertz, this asymmetry becomes insignificant. Okay, this asymmetry becomes insignificant, but at the low PWM frequencies, synchronization of the control signal is important. Synchronization of the control signals is important. Okay, next, coming to the third observation point. So with a fixed sawtooth wave, increasing the magnitude of the sine wave will increase the conduction time of device 1. Okay, and decrease the conduction time for device 4 for the positive half cycle, and vice versa for the negative half cycle. Okay, so here I am taking fixed sawtooth wave. So when we take the fixed sawtooth wave, it increases the magnitude of the sine wave, will increase the conduction time of the device 1, and decrease the conduction time for device 4 for the positive half cycle, and vice versa for the negative half cycle. Okay, next, this means that the fundamental component of the AC voltage, that is VAN, V suffix AN, and hence the output AC voltage will increase with an increase in the magnitude of the control sine wave and decrease with a decrease in the magnitude of the control sine wave. Okay, this means that fundamental component of the AC voltage, that means VAN, and hence the output AC voltage will increase with an increase in the magnitude of the control sine wave and decrease with a decrease in the magnitude of the control sine wave. So for control sine wave peak less than the sawtooth wave peak. Okay, so I already said that in the previous diagram. So we seen that two waveforms. In the first waveform we have two waveforms. One is sine wave and another one is sawtooth wave, and lastly we will have square wave. Okay, so for control sine wave peak less than the sawtooth wave peak, the output AC voltage varies linearly with variation of control sine wave, with the variation of the control sine wave. So coming to the fourth point, as the control sine wave peak equals the peak of the sawtooth wave. So previously, for control sine wave peak less than the sawtooth wave peak, the output AC voltage varies linearly with variation of the control sine wave. But here the control sine wave peak equals the peak of the sawtooth wave. The middle notch in the AC output voltage disappears. The middle notch will be disappear. Okay. Next, so if the control sine wave is increased to a higher and higher magnitude, more and more notches will disappear, and the output voltage will eventually become a single square wave per half cycle. Okay, so from that one it is clear that the AC output voltage can be controlled from 0 to maximum. 0 to maximum. So the sine wave itself can be modified with notches, etc. Create other effects on the waveform. Okay, the sine wave itself can be modified with notches. Why? Because to create other effects on the waveform. Okay, and next, so the order of the harmonics present in this type of PWM waveform is determined by K1n plus or minus K2. K suffix 1n plus or minus K2. So here K is the frequency multiplier. That means I already said that we are taking 9 square waves. So already I discussed on the waveform. So here the K is the frequency multiplier of the carrier frequency, and N and K2 are integers. Here N and K2 are integers. Okay. So however, K2 may only be taken up to 2. K2 may only be taken up to 2, after which the magnitude of that harmonic order becomes rather small. That's why the K2 only be taken up to 2. That maybe. Okay. Due to half cycle symmetry, all the even order harmonics also disappear. So due to half cycle symmetry, all the even order harmonics also disappear. So furthermore, in a three-phase bridge circuit, all of the triple harmonics, that is third, ninth, are eliminated. Triple harmonics are eliminated in the three-phase bridge circuit. Okay. Next, also, if the carrier frequency is a multiple of 3, even the harmonics of the order of the carrier frequency are cancelled out in the phase to phase and phase to the floating neutral voltages. Floating neutral voltages. Thus, for the chosen frequency multiplier 9, the order of the harmonics is given as 5th, 7th, 11th, 13th. So here all the harmonics except the even and triple harmonics as per the 6 pulse 3-step converter. Okay. So here I am taking frequency multiplier 9. So based on that, the order of the harmonics like this, that means 5th, 7th, 11th, the all are odd harmonics as for the 6 pulse 3-step converter. 6 pulse 3-step converter, that is minus Vd by 2, 0 plus Vd by 2, like that we have. But we are consisting of 6 pulses. Next, so however, in the PWM, that means pulse width modulation case shown, the 5th harmonic will be very small. 5th harmonic will be very small. So for that one I am taking one diagram. So it shows PWM output voltage waveforms corresponding to a PWM frequency of 3 times the main frequency. 3 times the main frequency. So this is the diagram I am showing. So it consists of phase to floating neutral and one phase to neutral and one phase to neutral, that is VAN, VBN, like this we have. Okay, and next phase to phase also VAB. Okay, like that we have. So here the diagram shows PWM output forms corresponding to a PWM frequency of 3 times the main frequency. The first waveform shows the control signals similar to those in the 3.11, that is a PWM first waveform. Okay, and second waveform is the phase A to DC neutral voltage VAN. Second waveform is the phase A to DC neutral voltage VAN. First waveform is control signal. Okay, first waveform is a control signal and second waveform is a phase to neutral. And next, so it is seen that it has one notch in the center of the each half cycle, and the width of this notch is dynamically controllable every half cycle. Okay, and next coming to the third waveform. So the third waveform is VBN. The third waveform is VBN. So the output voltage of phase B to DC neutral voltage, which obviously is the same as VAN, except the phase delay by 120 degrees. The only difference for the VAN diagram and VBN diagram waveform is the phase delay, phase angle, that is 120 degrees. So here subtracting VBN from VAN gives the phase to phase voltage VAB as shown by the fourth waveform. So fourth waveform is appear because of the subtracting of second and third and second waveform gives the phase to phase voltage VAB as shown by the fourth waveform. So this shows two notches resulting from the crossing of the control signals. Crossing of the control signals. That is the fourth waveform. Okay. Next, the next waveform is that of the VAN. So the voltage between the floating neutral N of A, star connected floating secondary, and the DC neutral. So this is obtained by adding and averaging the three AC voltages, that is VAN, VBN, and VCN. So VCN is not shown here in the waveforms, but subtracting VNN, VNN. Okay, that is the floating neutral. Capital N means floating, sorry, midpoint neutral. Small n means floating neutral point. Okay, so subtracting VNN from VAN gives the last waveform. That is the last. So this waveform. Transformer phase to neutral voltage. So this one, last waveform. Okay. So because of the half wave symmetry, all the AC waveforms are free from even harmonics. So because of the half wave symmetry, all the AC waveforms are free from even harmonics. Okay. Next, so waveforms VAB, that means phase to phase, and VAN, that is a phase to floating neutral, are free from triplen harmonics. Okay, VAB and VAN, and the VAN lags VAB by 30 degrees. Okay, combining these two waveforms through separate Y, that means star and delta connection transformers, will result in a 12 pulse converter, so which will have adequate flexibility of rapid AC voltage control without having to change the DC voltage level. Okay, DC voltage level. So the control of the DC voltage can then be optimized for other considerations. The control of the DC voltage can then be optimized for other considerations. So it should now be obvious that the AC voltage waveform can be chopped in many different ways with different control waveforms and numerical program. Okay. Next, there are a variety of waveforms other than sinusoidal and sawtooth, okay, that are used to create AC output voltage with fewer low frequency harmonics and fewest notches. Okay, so while chopping of the waveforms and showing PWM waveforms is easy on paper, okay, but it is not a trivial matter when we consider its implications for design of high power and high voltage converters. Okay, it is not a trivial matter when we consider its implications design of high power and high voltage converters. So in terms of switching losses, impact of increased higher harmonics, EMI, audible losses, etc. has to be justified by appropriate gains in other areas. Appropriate gains in other areas. Okay. Next, particularly if it helps satisfy the harmonic requirements without having to go to a pulse number higher than 12 for modest size converters. Modest size converters. Next, nevertheless, a considered use of PWM or notches at low frequency level has its merits, particularly for the fax controllers of lower power levels of say 10 to 50 megawatts. Okay, here I am considered use of PWM or notches at low frequency level. It consists of merits, particularly for the fax controllers of lower power levels of say 10 to 50 megawatts. Okay. Okay, thank you. So this is the topics for a 3-level converter with parallel legs and PWM converter. Okay, thank you.